morning doing my hair and the wind just ruined it. My beard too. All caught up in the windstorm out there. All right, good morning, everybody. Time for another KW production of Organic Chemistry with Dr. White, starring Dr. White. I was working on video. By tonight, I should be caught up for everything except this week. That's online. I think this week I'll have online through yesterday. And hopefully the quality's getting better. If not, I'll do Google. For those of you who had lab yesterday, I forgot to mention, and I'll mention before next Tuesday, and I'll give you extra time at the end of the lab to do the questions. First question, you have two choices. I talked about. Second question, you need two equations. And I'll discuss that in lab. All right, let's get going. If you checked your email yesterday, or this morning, or looked online, Blackboard, you'll see I posted an announcement, and the announcement is on 3/16/17, which is a week from this Thursday, tomorrow will be test number 2. Test number 2 has 9 pages, 10 problems. Some of the problems are multiple part, but no problems are multiple choice, except for the ACS final, which I don't write, have no control over. None of my tests have multiple choice. And it will cover alcohols, thiols, ethers, ethylene oxide, aldehydes, and ketones. I'll finish all that today. As a point breakdown, general knowledge, 11 points, nomenclature, 34, reaction 60. It adds up to 105, which means there's 5 bonus points on there. And let me remind you, nomenclature questions are, here's the structure, get the IUPAC name, or here's the name, including general names, draw the structure. And reactions, there's one main type of question. Here's give the organic product or products for the following, but I believe I have on this test 3 questions. Give the starting material or starting materials, which I call. Then we practiced everything we will today. That will be on the test, so that gives you plenty of time to prepare for it. That's part of my golden rule of teaching. I hated when I was a student. Teacher 2 days before the test finishes up material that will be on the test. How can you practice it if you don't have enough time? All right, with that in mind, a couple of upcoming events. On Monday, I will go through the ketones and aldehydes problem set. On Tuesday, back by popular demand, I will give my world famous review for the next test. In this case, test number 2. And some students say it helps them. I highly recommend you be here next week, and this week too. All right, any questions on test number 2? Don't be like test number 1, the problem says. Nothing new, I don't do surprises, but I let you know what you can know. And let's get back to ketones and aldehydes. But before I do this, did anybody happen to look at a bottle of rubbing alcohol and see isopropyl alcohol and say, or 2-propanol? I said, a few of you, ooh, that's an alcohol? I know the structure. Or do you happen to look at a bottle of nail polish remover and see it's got acetone, which is a ketone? This is a tough group. I will not give up. Remember, when you walk outside the door there, organic chemistry is all around you. By the way, if any of you saw SpongeBob episode where he does this. Use your imagination. That's my statement. All right. Yes, I do like cartoons. Little boy, he hasn't grown up to that. Except they're not as violent as when I was a kid, which made them better. All right, let's get back. I went through, I think I started doing this. Did I give any examples to the listening? All right, since I did, let's do one more. This pen's dead. And since I've already done this, I'll let you try right off the beginning. Have some fun. What's the organic product or product? Sort of follow it. And I believe I kept my promise to myself by test number 2 last week, or so I think I'm pretty sure I got it. I know I didn't use some faces, so you're no longer anonymous students in the class. But real people. All right, looks like everybody's done. Let's take a look at this. By the way, I've been secretly inoculating you against chemistry instructor's favorite trick on the test, and that is put a big scary molecule and the students go, oh, what do I do? Hopefully if you've been inoculated, which I've been doing to you, you don't do that because you look at this and say, what's different? Oxygen is different. Double bond to carbon. Carbon's here, carbon's here. This is a ketone. Could have been an aldehyde, but it's not. It's a ketone. I'm reacting with lithium aluminum hydride. Second step, acid and water. And what happens? You break the pi bond, and similar to hydrogenation in the product, what is will only attack carbon-oxygen double bonds, not anything else. So what does this tell you? Whatever attached to a carbonyl carbon will still be attached. So I can draw my ring in the isopropyl group here. Which is the carbonyl carbon, carbon double bond to oxygen, that one. And always keep your eye on the carbonyl carbon, because 90% of the time that's where the fun stuff happens. That carbon is this carbon right here. You don't have to draw it on the test. What happens? You break the pi bond, each atom gets a hydrogen, you don't show it on the ring, and that's the product you get. And that's how you do reduction with lithium aluminum hydride. And as I said yesterday, that was a great achievement. This with sodium borohydride, which I used to teach, but I don't anymore. This is good enough. That H.C. Brown of Purdue, Dr. Brown, won the Nobel Prize in chemistry in 1978 for this and other reactions that lithium aluminum hydride undergoes, which is a great achievement. All right, quick thing. I forgot to take this out. I'm going to skip this slide. We'll come back to it next chapter, carboxylic acids. This will not be on test number 2. It will be on test number 3. One of these days I'll remember to take it out. All right, got everybody's attention. Next couple of slides, I'm turning the switch. Will this be on test off position? But this is background information which will help you understand an important reaction. Then I'll turn the switch back on. Also, I should warn you, it looks like I'm having way too much fun. I am. All right. When we talk about ketones and aldehydes, something I haven't mentioned is if we put up a ketone or aldehyde, I'll use a special example. The carbon bonded to the carbonyl carbon is called the alpha carbon. That won't be on test, but it is terminology I'll be using in a little while when I do have a reaction. And it turns out there's something called enol-ketol tautomerism. And what happens is you shift the hydrogen and electrons to form this. This is called, because ketone or an aldehyde in ketone form. This, what do we call double bonds? E, E-N-E ending. What do we call alcohols? O-L ending. Put it together. This is called the enol form. And this tautomerism exists back and forth all the time in ketones and aldehydes. And what that means is something very special. I mean, really special. Stuff I did my PhD thesis on, so it's really special. And that is the alpha hydrogen, hydrogens on the alpha carbon are acidic, meaning you can pull it off with a base. Which, unlike hydrogens on CH2 and alkanes or other molecules, you can't very easily. It's real hard. This is not. Alpha carbon. The hydrogens there are acidic. What does acidic mean? Proton donor. If I react it with a base, what can I form? This anion. I'm not showing the count cation. It's usually one of the alkali metals, cations. And this is called the enolate anion. Again, switch is still click off, but this is quite important, especially to Dr. White. And you can draw what makes it stable. Well, based on the keto-enol form, I can do the following resonance form. Move this electrons there, that, and you have this resonance form. And both of these are called the enolate anion. They exist at the same time, just like the bonds in a benzene ring are holding hands. The p electrons are all connected together. And this makes the enolate anion more stable, which is why these are very acidic. My PhD work, I'm going to say something you won't understand. Most of the people, even the chemists in this building, won't. I did extensive research on cross-conjugated, kinetically favored enolate anions. And that was my PhD thesis. It wasn't the title, but that was the bulk of the work. So I'm a world authority in enolate anions, so I'm having a good time now. And what makes the enolate anion very interesting is when this carbon has a negative charge, it says, wow, I'm not happy. I'm looking for something that has a positive charge so I can bond to it. And enolate anions And I'll only teach you one reaction. There are others. But one of the special ways you can make carbon-carbon single bonds, which is always very special. Click, switches on, and let's talk about the aldol condensation. The aldol condensation deals with enolate anions. In fact, let me use this board because I'll need more room. Everybody have this down? You don't have to, going once, twice. And the aldol condensation deals with aldehydes and ketones. For my class, I'll only ask you to learn for aldehydes. And also, I'll give you a little special gift. Normally, just write one aldehyde or sometimes a 2 in front of it, but I'll draw both of them. Now, on the slide, I should have put either water or ethanol. In a couple weeks, you'll do an aldol condensation in the lab, and you'll be able to make carbon-carbon single bonds. It'll be fun. All right, what happens, the product, this molecule, you lose a hydrogen from the alpha carbon to form the enolate anion, which attacks the other carbonyl to open it up to an alcohol. And I'll show the mechanism, only because Dr. White wants to have some fun this morning. What really happens have this base plus one of the aldehydes, the alpha carbon, forms the enolate anion. This is a very powerful nucleophile looking for a positive charge. Where is there a positive charge? Carbonyl group. Carbon double bond to oxygen, positive charge. I have my other aldehyde. It attacks it, opens it up. This is a very strong base. I add water to that. I'll get that alcohol, and that's called the aldol condensation. Why aldol? Well, aldehyde, alcohols, OL, put them together, you get aldol. And what's special about this is a way of making a carbon-carbon single bond. Very rare, very special, very fun, lots of fun. And the question would be, what's the product or products or following reaction? And you look at this and say, what's different? Ooh, aldehyde. And Dr. White's gift to you on a test, 2 of the same aldehyde. I'll bet you that's the aldol condensation. What happens? You form the enolate anion of one of these and attach the other. So what do? You write the first aldehyde, remove a hydrogen, have it attack the carbonyl carbon of the second aldehyde, and it forms an alcohol. Whatever attached to it is still attached to it. Oops. And from the general reaction, this is R. And that's what you get. All right, let me help you out with this problem before I let you try it. Does anybody here know a reaction of benzene ring with sodium hydroxide and water? Because I don't. This is R. Why don't you try this one? What's the product or products for the following? Getting into the real fun stuff. I'll give you another 18.76 seconds. All right, time's up. Let's take a look at this. How do you do this? Well, first of all, what's different? Carbonyl. Hydrogen, carbon, aldehyde. Ooh, the same aldehyde. Reacting with base and water. And that's an aldol condensation. And what do you get? You form the enolate anion, the alpha carbon. It attacks the other carbonyl, forms a bond, opens this up, because you can only have 4 bonds to carbon, to an alcohol, and you have the first aldehyde form a bond from the alpha carbon to the other aldehyde, carbonyl, open it up to an alcohol. What's-ever attached to it is still attached to it, the hydrogen, CH2R. What's my R group? Benzene ring. Here's my alpha carbon. It will attack that, so I'm going to draw this molecule first. Remember, you formed the enolate anion, so you can take off one of the hydrogens. I'm going to write now the world's longest and ugliest carbon single bond to give me enough room. I have my other carbonyl, which opens up to an alcohol. And what's ever attached to it, CH2 in this case, and a benzene ring, And notice in one step, with a small molecule, I've made a very complex molecule by making something special, something rare, a carbon-carbon single bond. Yes?
So the hydrogen, the other hydrogen from the enolate anion goes
To the water, to the base. What
make
you also form here is water.
Okay. But is the hydrogen going for, like, towards the alcohol?
All right, here's what,
Or is it, do you not really see it when you're writing?
one knows it can come either that way, more likely since the water's around, it will come from the water.
Okay.
Because you usually have either alcohol or water, which is a proton source. And therefore, if we look at this, this will react with that, and that will form water. And then, does it come from that one or another water molecule? I don't know. And you couldn't really do with that something I don't talk about in this class, and that's using deuterium labeling. There's a form of hydrogen called deuterium, another isotope of hydrogen, which in certain reactions that I've done it, you can put on certain molecules and follow it by special equipment, nuclear magnetic resonance. This one, I don't think you could, because you can make water either way. It's coming from the water. Did that hydrogen come from the water made from base with the enolate anion, the hydrogen, the alpha carbon, or other water molecules? Don't know. I would bet other, but you've got a whole ton of them, or actually bowls of them. Whenever you use water, most of the time you have at least 50 molar solution, which means there's a lot more water molecules than anything else. I don't know if that answers your question, but that's probably the honest answer. All right, time for another small gift from Dr. White, and that is I will never put a synthesis problem on a test using aldol condensations, because up to now that's still considered cruel and unusual punishment by the Supreme Court. That might change in a couple of months, but not now. All right. Uh-oh, I'm at the end. And something I think that would help you out, let's go back and do some instant replay. And instant replay, I'd like to do the next 4 reactions, which for some reason students have difficulty on test 2. So I like to go over them more than once. And hopefully you won't have difficulty on test 2. Probably tomorrow I'll be going through carboxylic acid, so if you print out your notes, I might do it a little today. I highly recommend you print them out. It will not be on test number 2, but it will be on test number 3. If we take an aldehyde or ketone when R prime is a hydrogen, aldehyde, when R prime is carbons, ketone, reacted with 1 molecule of alcohol or 1 mole with acid catalyst, what you get is a hemiacetal or hemiketal. Remember, keep your eye on the carbonyl carbon, that's where the fun is. And whatever was attached to it is still attached to it. You break the pi bond, the oxygen gets a hydrogen from the alcohol, and then this carbon gets OR from the alcohol. The carbon that's bonded to the hydroxyl group is the carbon bond to the R group there. And why don't you try the following? React the following, and know that is cyclohexane, not a benzene ring. And what's the product or products for the following? Since I've already gone through the reaction, I'll let you try it, then I'll do it. date, don't forget to sign it. And don't forget when you're done, look up and smile. All right, looks like everybody's just about last hydrogen's going down. Done. Let's take a look at this. What's different here? Ooh, carbon double bond to oxygen, hydrogen here, carbons here, aldehyde. I'll call this my R prime, this my R double prime. Carbon, ooh, hydroxyl group, this is an alcohol. And I'll call this R. Keep your eye on the carbonyl carbon. I'll draw that first. What's attached to it is still attached to it. My cyclohexane ring, my hydrogen, will have a hydroxyl group. And then oxygen, what's my R group? N-propyl. Carbon has the, N-carbon has the hydroxyl group, so the N-carbon will bond to this. And now you guys can see it too. And that's how you do it. Anybody have any duct tape? I'll just put the screen on. I don't think the school will like that. Better? And let's go to the next reaction I've already talked about, but I'd like to cover it again. If you take an aldehyde or ketone, when R prime is a hydrogen, and now reacted not one, but two molecules of an alcohol or moles, an acid catalyst. Again, keep your eye on the carbonyl carbon. That opens up to, first of all, whatever attached to it is still attached to it, R prime and R double prime. And now on that carbon, you have two OR or alkoxy groups. And why don't you try this one? What would be the organic product or products for the following? All right, let's take a look at this. Question is, what's the organic product or products for the following? Look at what's different. I can't point anywhere else. What's not carbon, what's not hydrogen, oxygen double bond to carbon. And notice I have carbons here and here. It's a ketone. I come over here. What do I have? Carbon, hydroxy group, alcohol, and I have two of them. What with acid catalyst? What happens? Take a look at the carbonyl carbon. What's ever attached to it is still attached to it. What's attached to that? This ring. You can call one side R, the other R prime, the other R double prime. So I still have that ring. Here's my carbonyl carbon. It's going to have two oxygens. What's my R group? Ethyl. And that's how you do that. Now you can hydrolyze the following molecules with acid and water. And as I talked about it, where do you find acid and water real quick in this room? Your stomach. Oh, by the way, non-organic, but chemistry stuff. I don't know about you, but when I came here, it was real windy. You know, it probably still is windy. Did anybody think of you're getting hit in the face and there are other places by molecules of oxygen and nitrogen? And that's what you're feeling? That's chemistry too. Not organic, but still chemistry. The question is, what's the organic product? Product general reaction. What's different? Two oxygens on the same carbon. It's rare. I only know two places it happens. Hemi-acetal, hemi-ketal. One of the oxygens has hydrogen. The other has carbons. When you react it with acid and water, you get back the aldehyde or ketone you would have used to make that, which we just went through, plus the alcohol you would have used to make that, which we just went through. So, why don't you try this one? So I see the last hydrogen's going down. All right, let's go ahead and do this. And the question is, what's different? Ooh, oxygen here, oxygen there. One has a hydrogen, hydroxy group, and the other oxygen has carbons in the same carbons. Hydrogen, carbons here. It's a hemi-acetal. Acid and water, you get back the aldehyde and the alcohol or ketone, plus the alcohol you would have used to make that. I'll call this R prime, R double prime, and this R. And what do you get? Keep your eye on this carbon with 2 oxygens, becomes this carbon. What's attached to it? Our double prime methyl, our prime hydrogen, you get that aldehyde. The alcohol, which I'll write up here so people over here can see it, and that is, notice the oxygen is the center of 3 carbons. Quick review, do you break carbon-carbon single bonds? No. So I still have my 3 carbons. And notice the oxygen is the center one. You can draw this different way, but either any way you draw it is 2-propanol or isopropyl alcohol, and that's how you do that. And finally, if you have an acetal or ketal, which I won't ask you on test, but when R prime is H, it's an acetal. When it's carbon, it's a ketal. React with acid and water. When you get back the aldehyde or ketone you would have used to make that, plus the alcohol you would have used to make that. As you've seen on test number 1, my problem sets, I ask, give the organic product or products. I don't ask for you to balance them. Therefore, do you have to put a 2 here? No, but a lot of students get upset if I don't, so I don't need students upset at me, so I'll put it in quotes. But you don't have to on the test. And why don't you try this one? All right, looks like everyone is about done. So let's take a look at this. What's different? Ooh, oxygens. 2 oxygens to the same carbon. Each oxygen has carbons on it. That carbon right here has carbons on it. What do we have? An acetal or ketal, in this case a ketal. I can call this R prime. And this R double prime, doesn't matter what. But the key thing is, when you react it with acid and water, what do you get? You get back the ketone or aldehyde you would have used to make that, plus the alcohol you would have used to make that. This is my R group. And therefore, I keep my eye on that carbon, because what's ever attached to it is still attached to it. This ring is going to become a carbonyl. My R group is methyl. For those of you who are inclined, you can put a 2 there. I wouldn't. And that's how you do it. Let's do one more that students sometimes find challenging. Grignard, most people get easy. This one, let's do one more. Take an aldehyde or ketone, react it with the Grignard reagent. That's the nucleophile. It will attack this, open it up to an alcohol. And you've done something very special. Very important. You made a carbon-carbon single bond. And why don't you try this reaction? What would be the organic product or products or power? Notice you're doing organic chemistry, quite sophisticated organic chemistry. I hope you enjoyed and was beneficial my instant replay. See all the wonderful things that all right, let's take a look at this because the clock is ticking, or at least moving. What do we have here that's different? Carbonyl. They're carbonyl carbon to oxygen, or carbon oxygen, carbonyl group, hydrogen carbons, aldehyde. Could have been a ketone. And what is this? I'll call this R prime, this R double prime. What's different here? Magnesium halide, and that's a Grignard. This is my R triple prime. Keep my eye on the carbonyl carbon, because that's where the action is. What's ever attached to it is still attached to it. Hydrogen, methyl, I get an alcohol, and now I do that special thing. I make a carbon-carbon single bond. What's my R group? 2 carbons. And that's the alcohol you get. Now, one of the things, a Grignard-like reaction reacts with a cheap molecule to make a molecule that I couldn't get any other way that allows pharmaceutical companies to make a product called the birth control pill. We'll talk about that later in the semester. For those of you at lab tomorrow, don't forget, wear a long sleeve top or lab coat. With that, I'll let you out a whole 35 seconds early.